Okay, so here we have something that is also problematic, because if you see the integrand in here, if it's just sine times cosine, that was our first problem. That was problem number 1 from this section. We handled that just fine. It was the same angle in here. But here you have 5x and 4x. This is really a problem for us because I can't get by with a basic u substitution. The derivative of sine 5x is cosine 5x times 5, but you can't cancel out a cosine 4x and a cosine 5x. This is a problem for us. So what I'm going to do is use the bottom of the page of page 1 of our notes. Again, these are all just trig identities, which means they're equivalent statements. So I'm thinking about these guys of the first page. This is the very, very bottom. So I'm going to look at the one that has sine and cosine together, which is that middle one. Now, this is a pretty complicated statement here, but I want to write down its equivalence. So what I have here is m is 5, n is 4. How does this work? Well, I'm going to convert it over to, I'm going to have a 1/2 in front of the whole thing. It's going to be sine of the subtraction of them, so 5 minus 4 would be 1, x, right? And then plus the sine of the addition of those two things. So that would be sine of 9x, and that's a legal swap of what I can do. Okay, so I'm going to replace that. And I'll just kind of write out what I'm saying here. I'm saying that m is 5 and n is 4. We're looking right there for those coefficients to use that identity. So this is appropriate or equivalent to say, I'm going to use a trig identity here. This is going to be the same exact thing as a 1/2, and then the way this identity goes, it's the sine of the subtraction, and then I have plus the sine of their addition. There it is. So now I can integrate this and work on it. So I've got 1/2 sine x, and then that 1/2 carries here too. So I'm just kind of splitting the integrals here to work on it. Okay. So the first guy, I can come up with an antiderivative pretty quickly. The integral of sine is negative cosine. So all I have to do is throw a negative on here, and I'm done that part. Over here, I have to employ a little u substitution, so let's show that. I'm going to let u equal 9x. I'm going back to basic Calc 1 strategies. Let u be something inside something composite. Its derivative is 9, and so when I come in here and try to work on this integral, of course I have sine u, and in place of dx, I'm going to legally have du over 9. So this integral transforms into 1/18 sine u du, which again, the integral of sine is negative cosine, so I've got it. It's negative 1/18 cosine u. I'm just going to put these two puzzle pieces together because, of course, I should be able to work on this and put everything back in terms of the x variable. So my final answer here, I'm going to kind of put it off to the side over here, draw a line. Part of my antiderivative was negative 1/2 cosine x. I got that really quickly. And my other part is negative 1/18 cosine 9x. And that constant of integration working out there. Okay, so just kind of working on some of these other more interesting integrals that you may see. And again, trig identities are important because they come up from time to time. So I'm going to take a look at 11, which you can kind of see here. Let me see if I can put that line in a better spot so it's not, well, ruining too much there. I say I have cosine 5x, cosine 3x. This is, again, another problem because you have different angles here. So I'm going to go back to that, bottom part of our first page of our notes. And the guy I'm looking at here is the last one. You see this cosine mx, cosine nx. Very similar structure here on how we're going to set it up. We've got the 1/2, we've got the cosine of the subtraction, plus the cosine of the addition. So I'm just going to be really clear again. I'm saying m is 5 and n is 3. And the way that I'm going to work on them is I've got this equivalent statement that I'm going to write. There's a 1/2 in front of everything. And I'm going to have cosine of the subtraction. That'll be 2x. And then I'll have plus cosine of the addition. So that 1/2 is carrying through both of those terms. And I can handle them piece by piece. So what I really have is this. I can handle that piece. Now remember that 1/2 is still carrying through to this cosine 8x. And for each one of these, they're separated, and you're going to do a separate u substitution on each of those guys. So here I'm going to let u equal 2x, and here I'm going to let u equal 8x. And I know a lot of you probably do this kind of basic u substitution just in your head. You know what the follow through is, and you sort of go for it. I'm going to show the work because that's what I do. You can jump ahead in the video. So I have these extra coefficients, right? I'm really kind of maneuvering this around. This is 1/2 cosine u, and then 1/2 du. This guy over here is 1/2 cosine u, and then 1/8 du. Okay, so I can pull those two 1/2s out. That's going to be 1/4. The integral of cosine of u is sine of u. And I'm just going to switch. I said that u was 2x, so there I have it. I'll do the same thing over here. I've got a 1/16 as my coefficient, and then I'm really integrating cosine u du, which again is sine u, and u was 8x. And you're good. So these trig identities are insanely useful when you're up against really complicated looking integrands. All right, so we have a few more that we're going to tackle. And again, these are a lot of examples. Maybe you don't need all of these examples, but I like to show you a little bit of everything so that you get a good feel and a good amount of practice in on each of these. Okay. So here we have tangent to the fourth. If I go back to that page, there are no secant factors. I'm looking at the third option there on secants and tangent. No secant factors, and the power of tangent is even and positive. We're going to convert a tan squared factor to secant squared and expand if necessary. So we're going to do this piece by piece. So here's what I'm going to do. I'm going to take a look at this and say, all right, let's reimagine tan to the fourth. That, of course, you could write it like this. So this is one of those things you do piece by piece. Convert a tan squared factor and see what happens. So let's take this guy and let's reimagine that. Tan squared is the same exact thing as secant squared minus 1. Let's see what that looks like. I haven't done anything wrong. I'm going to see if it gets me to where I'm going. Okay. And so let's look at it. Let's see what I would be able to do in this particular case. I think I'm going to maybe carry through, let's see, I'm still blue, tan squared x, secant squared x. Let's just multiply that tangent through, that tan squared. Let's see if that helps. I think so. So here's what I'm going to do. I'm going to actually break these into two separate integrals, like totally separate from one another. So let's see what I can do on this. Right over here, I'm going to get this to work pretty nicely because the derivative of a tangent is secant squared. This is going to be great. I'm going to do a u substitution on this. I'm going to let u equal tangent. Its derivative is secant squared, which I see here, so that's pretty great. If I let u equal tangent, then that means tan squared there. That's u squared. Now that secant squared was already there. I didn't mess with that. But my du follow-through is perfect. This is exactly what I want because that kind of gets rid of your secant squared. This is great. You're integrating u squared du, which we all know is 1/3 u cubed. So I actually have part of my antiderivative here. Part of my antiderivative for this entire problem looks like that. Now I have to make sure that I do the other guy that I kind of ignored over here. I kind of like, wait, what's going on with this guy? I don't want to forget about it, right? So how do I do tan squared? I think we already did this one. Maybe I'm just losing my mind. But we have an identity for this. Look, okay, I do have this minus sign in the front. So I'm going to do this. Tan squared is the same thing as secant squared minus 1, right? That's our identity. Okay, so let's come at this again. The integral of secant squared is tangent. And the integral of 1 is just x. I have a double negative going on there. This is great. I have my answer. I have part of my answer down here that I worked really hard on with that u substitution. And then here I have negative tan x, plus x plus c. I'm good. Okay, so sometimes you have to get a little bit creative with it, but you really want to make sure that you know that your derivative rules and what kind of lays up to be a really good u substitution. That's an interesting problem. Okay, so let's take a look at secant cubed. This is the one and only on our sheet that was mentioning, hey, if you have an integral of secant that is odd and standalone, this is the one that we're going to likely need integration by parts. How is this going to work? Well, let's read. We're going to kind of take a look at this. This is in your textbook. I'm just going to talk it out. What I'm going to do is break up this integral legally. And let's take a look at this. We're gonna break this up into secant squared and a secant. And let's be honest about what's the easiest thing to do. I recognize secant squared as being an integral that is generally easy to work on. That I'm going to set that to be dv, because if I'm integrating secant squared x dx, which is what you want to do if you want to find v, right? Well, that to me is pretty complicated, but it's tangent. Now again, in integration by parts, I'm not going to put the plus c in here. Okay, but that's like the hardest part of your integrand there. That's a known. I can break that up and do the integral pretty quickly. What I have left over is I have that secant over here that was just kind of hanging out. Kind of ignored that. That must be the u then. I'll take its derivative. Okay, so let's get in here with integration by parts. And let's remind you what integration by parts is. It's u times v minus the integral of v du. We've been working with a basic u substitution this entire section. This is the one moment where your really fancy strategy of integration by parts is actually needed. So let's set up what our answer is going to be so far. Part of my antiderivative is just u times v. So that's secant x tan x. Minus the integral of v du. Okay, v du would be these guys together. Tangent times secant x tangent x. There should have been a dx up there. Okay, so what do I have here? Well, okay. That is tan squared x secant x. Okay, so I have part of my antiderivative and the other part left for me to work on. If I go back to what should I do, I'm a little confused on what I should be doing here. If I kind of look at this, what I'm going to do is I'm going to swap out tan squared. There's really no other option. I can't let u equal tangent because I don't have secant squared in the problem. I can't let u equal secant because its derivative is secant tangent. My only option here is to go back to using one of those Pythagorean identities. Let's rewrite tan squared as secant squared minus 1. It's an identity, so it's true no matter what. I'm hoping it's going to be helpful to us here. And let me actually distribute that secant through to everybody. What would that be? Secant cubed minus secant. And now let's actually like break this apart in a way. I actually see where this is going now. Secant cubed x. I have this minus in front of this term. I'm going to split it up into its own integral here. Let me kind of really note it that way. I'm going to put the dx there. And then this would be the integral of negative secant x dx, but that negative is in front, so that's going to change it to a positive. Okay. Now, let me just pause for a second and say, this is interesting. Isn't this the question I was supposed to be finding, right? Let's go back. Let me pull this down. I was supposed to be trying to find the integral of secant cubed. That's weird. I'm just going to draw a line. This is exactly what I'm trying to find. Interesting. We've seen this idea before. We've done this before. This is exactly the integral that I'm looking for, and it turns out in my work. What am I going to do? I'm going to add it to the other side of the equation. I'm going to get rid of it. So let's add secant cubed. So it annihilates this part of my problem over here, but whatever I do to one side of an equation, I have to do to the other side as well. So let's do it. What does that give me? It gives me 2 secant cubed x. That's 2 of what I'm looking for. Now, I already have part of my antiderivative here, that secant tangent. I just kept rewriting. That's part of your answer. I annihilated that middle component. And the integral of secant as a standalone, that has an actual antiderivative rule to it. It happens to be the natural log of the absolute value of secant plus tangent. Now, I'm not done my problem because I want to try to get secant cubed x by itself. All I'm going to do is just come at this and multiply every single guy by 1/2. That's going to knock out the 2 in this problem, right? But whatever I do to this side, I have to do to this term, and I have to do to this term. So my final answer here for the integral of secant cubed dx is going to be 1/2 secant x tan x plus 1/2 natural log absolute value of secant x plus tan x. Now you don't have to put a plus, like a 1/2 on the constant of integration. That's just kind of, it's just a constant. So who cares if there's any number multiplying it? There is my final answer. So this was that one moment on that whole flowchart of like, hey, you really need an advanced integration technique of integration by parts to really get in here. Everything else is a basic U substitution, but it's intentional. It's efficient. They're trying to be very helpful with, hey, here's the U substitution that's going to get the job done. All right. So here's our last problem of this section. Take your time and go through the section. Go slow. There's a reason I have just this one section. You know, chapter 8 is a lot of intense integration, so go slow. Here you have something like this. This is not anything that we've seen on any of the other examples. They were all like trig functions. Here you have a polynomial, right, times the secant squared. And so it's kind of like a little curveball. But I could have put this in our previous lesson if I really wanted to. None of my strategies from this section 8.3 are going to help me here. Nothing in this section talks about a polynomial and a trig function. Everything is just all trig functions all together, really interesting ones. I have to come at this and say, well, this is not going to be a basic U substitution when I have a polynomial and a trig function. I am going to have to declare this of saying, you know what, I think this as itself is integration by parts. Let me pick off the hardest part of this integrand that I think I know an antiderivative for, and that would be secant squared. I'm going to say that dv is secant squared x dx. Because the whole point here is, yes, I can find v, and I kind of knew that in my head. The integral of secant squared is tangent, so that's nice. That means the other parts of your integrand, you know, over here, that must be u. And let's just remind ourselves what integration by parts looks like. Remember, it's u times v minus the integral of v du. And right away, I have u times v. That would be x times tangent of x. What I'm left with here is the integral of v du. Now, you can either know what this antiderivative rule is, or you can prove it yourself, but this is the one we proved at the very, very beginning of this lesson. The integral of tangent happens to be negative natural log absolute value of cosine. I'll just get rid of that double negative. Okay, you didn't have to use that one. Remember, if you really wanted to, might as well come at it from here. What if you said, oh, I didn't use that one. I decided that the integral of tangent was positive natural log secant. This is also amazingly perfect. Okay, so you want to try to be fluid and flexible. And so I'm trying to end this lesson with integration by parts, because you're going to have to diagnose these problems. You're a doctor. You're gonna see this. It's like you're a doctor. You're gonna see this integrand and have to be able to figure it out. Is it basic use substitution? Is it integration by parts? Do I have to use a fancy trig substitution? Let me see where things are sort of going from this trig identity idea. All right. So definitely take your time on the section, and hopefully you have enough example problems here to get you out of any sticky situation.